reader. But I have something weird here. Because if you look at this, you see actually that it is not the nonce reader which is replied. You would expect that, like nonce tag, and then the reader shows, oh, I can do something with that nonce and I'll send it back from the tag. And then the reader sends his nonce, and then the tag should actually say, oh, I can do something with that number from the reader. But what it does something with its own number, which is sent earlier. So that's really strange to see in the beginning, but well, they chose for that for some reason, I guess. I don't know, they didn't say why, I guess. What is a mistake we came around? There are so many cards in the field that are using default keys. That's really worse. I mean, there's so many, if you look at these keys and you try them on your card, on all the sectors and blocks you have on your card, then if you have like 90% chance that it will actually hit some block which is using manufacturer keys. Maybe it's not storing really much information, but if you have at least this, then you can do some very interesting attacks, which I show in the end. Well, system integrators just seem to ignore the warnings which are given by the manufacturer even, that they should use these keys. Well, what is wrong with a random number generator? It's shown by Henryk Plötz in the CCC presentation that it was only, you could very easy get collisions if you power up, and actually it's only 16-bit entropy, so you have only 65,000 possibilities, and the thing is that it's really easy to get collisions there, and if you even can count on it when it comes back, you can, well, say, oh, I'll wait for a certain time, so, and now I'm back again on the number I want. Well, that was shown there, and that's very nice, but it's a really mistake in their design. What's another mistake is that what they did is it's actually a malleable cipher. It's maybe, I guess, for the crypto guys on the will understand, but I'll try to explain it a little bit. You have key stream, a one-time pad, so the random generator generates a one-time pad, and that's called key stream. Then you have, on the other hand, you have like plain text, and those are XOR together, and then you have cipher text. The thing is, if you can manipulate the random numbers, and you can reuse key stream, which is possible because the actually plain text is not involved in updating the cipher itself, the pseudo-random generator in this, then you can actually reuse key stream. It's totally independent on the plain text. So, and that's very interesting because a colleague of mine showed it already 2 years ago to me, that he was able to get information from a card because he listened to a transaction to a gate and a card, and then, well, noticed which randoms were used, and then replaying that later on the card and trying to manipulate to get the right random. And when he had it, he can actually query for a different memory block, and then he can read out the card without even knowing the key. Well, that's a pretty much startup, what we had at that moment. Well, it's another mistake is that the initialization of the cipher is kind of weird. They set the key into it, and then they load some information into it, which should be card dependent. You have the UID, which I also already named as the fixed identifier. Then you have the nonce tag, so the random of the tag, and the nonce reader. And those are loaded into the internal state before it starts generating key stream. But it is not loaded into with feedback from the cipher itself, so that the key will already influences what it's going to update. Now it's loading in that's pure, simple, and plain. And that means that you can actually switch with stuff. Like you can change your nonce a little bit. If you're playing the tag, for instance, then you can change your random. You can change the key you are working with. and then it will still work on the cipher. That's what Plötz also showed in a CCC presentation, which was, yeah, it's a weird mistake what they made, but they fixed it in a later product, which is, I guess, presented tomorrow in here. The high-tech is, I guess, a successor of this one. But well, if we look at the reader side, then there's another mistake. I mean, we came up so many mistakes we couldn't even count. It's like I tried to say here the major ones. The reader does no input validation. It expects that the text gives a random number, but we were able to actually send the random number as we wanted. We wanted, well, the random number was normally 32 bits, but we were like, oh, if we now just send a random number of 1 bit, and the reader says, well, okay, it's a random number, and you have sent it, so that's just what I'm going to work with. So that's a very low entropy for a random number. Thereby the reader really starts leaking information because he's only going to use so small a random number. There's no really randomness in it anymore. Even we were able to send a very long random number, longer than it should be, and you can update the whole internal state of the cipher. Well, that's convenient if you want to manipulate with the cipher values. Well, then I'm going back to that parity obfuscation part. I mean, we all know that a one-time pad is something you can lay against a plain text and you get cipher text, but you should do that one time because, yeah, it's a one-time pad. What they did is use a one-time pad twice in certain places and actually in place of a parity bit. They used from the next byte they are going to send, the first bit of that one is encrypted with a keystream bit. But that keystream bit is also used for the parity bit of the byte before that one. That's a little bit strange when I tell it maybe this way, but the picture shows how it goes. And this means actually that if you know, for instance, you know only the second part, the second byte you know, then you can, you know, of course, the keystream bit there. Then you know, oh, what was the parity there? And there you can say, oh, then I know if it was an even or an odd value. So it's actually leaking again a bit without even have to do that. I mean, it's a weird mistake they made, but well, for us it's kind of convenient, of course, to look at. Then what they actually did is they made a cipher. This is the cipher, and I don't know if you already seen it, but this is a linear shift back register in the top. And then there's some filter function and then produces keystream, and it does it 1 bit at a time. So it shifts 1 bit, it produces keystream, and then again. But as you can see, this part, the left part on the, does not really produce keystream. So that means that if you actually have an internal state and you have encrypted data over the air, which is used to update the cipher itself, and that is done during the authentication, you can roll back the linear feedback shift register, because if you shift 1 bit back, you can get the keystream bit out of it, and that's a really problem, because then you can actually, if they only used this bit for the filter function within it, then you could not guess that bit, but they just left